Okay, so welcome everyone to the Mitake Trend PD reading seminar. Today it's our great pleasure to have Professor Yeoneung Kim, currently at SeoulTech. He's gonna talk about solving non-convex Hamilton-Jacobi-Isaac equations in base policy iteration. Please, Yeoneung.
Uh, Thank you for the introduction. It's my great pleasure and honor to give a talk on this subject. Here is a table of contents. I'm going to begin with a brief background, brief background in neural network and physics-informed neural network, and then go into Hamilton-Jacobi equation and in the context of differential game. And then I'm going to introduce our algorithm and then provide some experimental results that validate our methodology. Let me start with a brief introduction on neural networks. So neural network is simply a composition of a linear function and some non-activate and nonlinear function called activation function. So the picture on the right describes uh, two a neural network with two hidden layers. So we call these circles node, and the first input layer receives a vector, and then and the value is propagated with the matrix multiplication. After this computation, it will go through nonlinear activation function, and this process is repeated. So if activation function is linear, then the neural network will be linear too, which is not good. So a standard choice for activation function is something like hyperbolic tangent or sigmoid function. And there is a theory behind this function structure, which is called universal approximation theorem. So it is known by Banco, well, 4 years ago, that any continuous function can be approximated by a neural network with one hidden layer with arbitrary precision. So given epsilon, we can always find a matrix Wi and coefficient alpha I such that the difference is within the error. So you can think of a neural network is just a function approximator determined by a parameters Wi and alpha I. Uh, do you have any questions so far? The neural network will be playing as a building block of our method, so I want to give a short stop at this moment. Can I move on? Okay. So uh, there's a innovative framework called physics-informed neural network, which is aimed at solving PDEs with neural network. So deep learning, the word deep learning sounds very fancy. It's just a neural network with many hidden with many hidden layers. So a great advantage of deep learning approach for PDE solving PDEs is that in many cases the methodology is scalable, unlike traditional numerical methods such as finite element method or finite difference method. So general PDE setup can be written in the following form. F indicates the PD operator, and B represents by a boundary operator. So in the framework of physics-informed neural network, the goal is to approximate the solution to PDE by a neural network and parameterized by theta. So theta here corresponds to Wi's and alpha i's, which are unknown to the user yet. So our goal is to find theta approximating UX accurately. Given function approximator, neural network approximator, we can simply throw it into PD operator and boundary operator to define so-called residuals R denoted by R and boundary PD residual R and boundary residual B. And combining them together, we define loss function, which is defined as L2 norm of PD residual plus um, L2 norm of boundary residual. We sometimes put a weight here, and such a weight should be determined empirically. So, right, expanding it out, you can, and so here, L2 norm in the whole domain is usually intractable. We use a sample points. We sample some points in the domain and also from the boundary to approximate the L2 norm of residual function. So, and then uh, and one great thing about the using neural network in solving PDE is that you can differentiate the neural network with respect to input variables xi's. And as mentioned, such a framework is very scalable to high dimensional space. So one important step in solving PDE with neural network is sampling. So uh, while PIN approach does not require a mesh, we need a random sample from the domain to define L2 loss functions. So, um, uh, looking at the figure on the right-hand side, so in this case, we consider a space temporal domain and general sampling scheme uh, follows the uniform sampling. So we just sample like many points, 1,000 or 10,000 points randomly from the prescribed domain.
Can I ask a quick question?
Yeah.
Yeah, so for the collocation points, I mean, for your problem, do you have
Mhm.
to fine tune it at some point, or you just select them randomly?
We just select them randomly, like thousand points at every 10 iterations of solving PDE.
Okay. Yeah,
Mm.
thank
So how I go into in more detail later, but let me quickly point out what you just mentioned. So one we start with a random, let's say we started with a 1,000 random samples. Then we compute the loss function given that sample, and we optimize it with respect to theta. And then after optimization, we sample another random 10,000 points again, and we repeat the process until the loss function converges to zero. So at the end of the day, we might have used like millions of points if iteration goes till 10,000 steps. So let me quickly point out the some fundamental differences between finite element methods and PINNs, where PINN stands for Physics Informed Neural Network. As I mentioned, FEA requires a mass generation, and it also uses piecewise basis functions. And then the computation is done via matrix inversion, which requires tons of memory and computational resources as dimension increases. On the other hand, in the framework PIN, we only use random sample points instead of mesh. And there are some theoretical guarantees um, covered by universal approximation theorem, theorem for neural networks. And optimization can also be done very efficiently on GPUs. So um, to increase the accuracy in the framework of finite element method, we just use finer and finer grids. However, in the framework PIN, we just sample more points. Now let's move on to Hamilton-Jacobi-Isaacs equation from a stochastic differential games point of view. As many of you are familiar with this framework, I introduced them very briefly. So in the differential game framework, we have a stochastic differential equation governed by the following form, where A of S, and we have two sets of a pair of controls, A of S and B of S, which should be determined to optimize the objective function. So control A minimizes the cumulative cost while B maximize the cumulative cost. Usually, beta is assumed to be non-anticipative, which means that beta does not assume the future behavior of a control input inside. With this objective function, it is well known that V is a viscosity solution to the second order Hamilton-Jacobi equation given as follows. So our goal is to solve a formation Hamilton-Jacobi Isaacs equation, but it's generally it's very challenging to solve such an equation accurately. There are a couple of reasons. One is that Hamiltonian is often non-convex or non-smooth with respect to the momentum. And also, the Hamiltonian, it also includes a two-step optimization, infimum and supremum. So, but particularly in high-dimensional space, FDM and FEM, suffers from cursive dimensionality, which means that it's generally not solvable in the dimension above five or more. So let's think about five-dimensional Hamilton-Jacobi-Isaac equation, meaning that it has five axes, and let's say we have 1,000 discretization, the 1,000 grid points in each directions, then we end up getting 10 to 15 grid points in total, which is not tractable at all. So, or as an alternative, policy iteration can be efficient in overcoming the first challenge, as policy iteration comes from linearization of a nonlinear PDE. So our approach is to combine the idea of policy iteration with with physics-informed neural network. This was a call from my wife. Oh my God. Sorry. Excuse me.
Yeah, you can mute yourself for 10 seconds or something.
Oh yeah. Maybe it's a some emergency thing should happen. Oh, I'm so sorry. Excuse me.
No problem, no problem.
It was just a random monitoring call from Korea. Sorry. Yeah. So policy iteration for a Hamilton-Jacobi-Isaac equation is given as follows. So fixing a policy, meaning that we fix two controls, A of n and V of n, and then we consider a linear PDE given as the following form. So looking at this PDE itself, it looks definitely easier to solve than the original Hamilton-Jacobi-Isaacs equation because it's linear. On the other hand, the policy of, once we solve for V of n given A of n and B of n, we update the policy A of n and B of n in the following this procedure. We first fixing B, we minimize with respect to A, and with this optimizer, we update B accordingly. So it looks pretty nice theoretically, but one caveat or difficulty in this framework is that it's still impossible to find a closed form solution to the linear PDE. It definitely it might depend on the structure. So if structure is really easy, then maybe a closed form solution V of n exists, but in general, such a solution does not exist, or we cannot really find such a solution. And there's another challenge in regard of the some degeneracy in diffusion term. So even if we are able to compute accurate solution to a linearized PDE, but we might suffer from measurability issue or degeneracy issue arising in diffusion term. So particularly when the diffusion matrix is degenerate, then we fail to have good properties in linearized PDE, such as monotonicity or comparison principles. And also, um, without the PDE is not enough elliptic enough, then the measure the we also suffer from choosing a measurable policy given in terms of a the momentum. So very recent work by Guo Tran Zhang show that uh, such a policy iteration um, is well posed after the discretization of the domain space and temporal domain. And it also requires a numerical viscosity for for stabilizing the iteration scheme. And they also showed exponential convergence and the explicit convergence rate in terms of the iteration step and the discretization level is specified in their work. So far, degeneracy might destroy the well-posedness of a PI in continuous setting, and uh, we will consider a strongly elliptic case instead. So, classical solvers require a domain discretization, leading to mass generation and refinement. But PIN can the PIN approach can avoid such discretization. So we expect that method is effective in high dimensional space as well. So there are a couple of important components. First, choosing random collocation points when solving PDE, linearized PDE, and it's a fully continuous formulation. So we are not going to use discretization at all. And that approach is supported by a fast um, uh, computation of differentiation operation in over a PyTorch library. But to do so, we are going to use a uniform ellipticity of a diffusion coefficient, and also we are going to use explicit Lipschitz feedback selectors which is needed in Palos update. And at the end of the day, we are going to prove global L2 convergence with respect to the residual loss. So, so let's see how it works. So we fix policy and we solve linear PDE with a neural network. So we are going to find a neural network approximating V of n as accurate as possible. But no matter how small the error is, we are going to end up having error as well. So it's impossible to make this relation hold exactly. So meaning that we are such an approximation always leads to some error, and we are going to get that point soon. And then once we find so approximate V of n, then we can compute the derivative V of n in an efficient manner as well. And another note here is that um, thinking of the structure of neural network, V of n is always smooth. Um, it depends on the choice of activation function. As long as activation function is smooth, for example, tangent hyperbolic function is smooth, the sigmoid is smooth. So when we use such an activation function, our neural network is always smooth. So there is nothing weird happening in finding a gradient of neural network. So to be more specific, we start with a random policy A of 0 and B of 0. And we are going to solve that PDE iteratively. And we solve the linear PDE with such fixed policy, which can be done by computing that object with randomly sampled collocation points. So we sample like the thousands of points, or thousands of pairs of TJ and XJ, and then we define we throw that neural network into a PD operator to compute the residual loss. So that is actually a pointwise computation to approximate L2 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 norm of residual function. So theoretically, we need to choose two sets of collocation points. First is from the interior, and the second is from the terminal. But by using some specific structure, we can always make terminal condition to hold, and I'll get to that point later. So in our algorithm and in our method, we don't need a sample. We don't need sample points from the boundary. And with those points, we are going to optimize that objective function. So some key distinctions from Guo-Tran and the work by Guo and Tran. We don't need artificial viscosity, which was introduced in their work for stabilization. And also our framework is fully continuous and mesh-free. And we also provide a global error bound for PIN approximation, which incorporates residual loss. So to get into theoretical results, I want to introduce uh, some assumptions on the dynamics. So we are given two control sets, A and B, which are compact and convex. So convex, such an assumption is critical because we are going to optimize the update policy in prescribed domains. So without the compact and convex assumptions, such optimization might be painful. So it's good to use a compact and convex domain. And as usual, Lagrangian is defined as a sum of cost function and dynamics times plus cost function dynamics times the momentum. And we are going to also assume that L is mu A strongly convex and mu B strongly concave to guarantee the regularity property of policy update. And also, we assume that G is smooth enough and integrable for some beta. And FC, sigma are all bounded and Lipschitz in all variables, and we also impose strong ellipticity assumption in diffusion. Let me quickly mention why such an assumption might be restrictive, but not that restrictive in the real-world applications. In the real world application, we somehow restrict our domain to a five bounded domain. Otherwise, there's no way to do computations. So in practical perspective, we can always assume that G or G, F, C, sigma, all functions needed for the dynamics are decaying outside of a complex set. So that's why such an assumption is not that hurtful in the application side. And under such an assumption, we have introduced a uh, pol policy update scheme given as this line. And one good property of such an update is that the policy update function alpha star and beta star are globally Lipschitz with respect to P. So such a regularity property guarantees the stable iteration. So one of our main theorems is that V and tilde is a approximate solution by a neural network, and V is a true solution of the Hamilton-Jacobi-Isaacs equation, and the L2 error between these two can be characterized with a term from residual loss, which arises in approximating, which arises in solving linearized PDE, and it has a contraction. So if residual loss is zero, meaning that we can solve linearized PDE exactly, then we get an exponential rate of convergence as expected. And um, um, and one other classical property is that assuming in theoretical side, in theoretical perspective, if a uh, linearized PDE is solved exactly, then Vn converges to the the solution to the Hamilton-Jacobi-Isaacs equations locally uniformly. To see this, we follow standard argument used in the literature of viscosity solution, saying that let's say Vn is a solution to the linearized linear Hamilton-Jacobi equation with a fixed policy of n and b of n. We have a nice representation for the value function from Feynman Keck formula, and and we can also show that V shares L infinity, uniform L infinity, norm and Lipschitz bounds, and 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 and, and then by Argela-Ascoli, we can show that V of n converges to V locally uniformly. So by the stability property of viscosity solution, uh, we get the result that V solves the original Hamilton-Jacobi-Isaacs equation. We just follow the well-established literature of the theory of viscosity solution to prove that property. And this approach was possible because our policy update is Lipschitz continuous and continuous. In Lipschitz continuous in momentum and continuous in other variables, T of x, by implicit function theorem. Uh, and moreover, so let me quickly give you a remark on that. So V of n is the exact solution, while V of n tilde is a approximate solution represented by a neural network. So let's focus on the key difference. So the previous theorem says that, and we not only get the locally uniform convergence of V of n to V, we also get the rate of convergence given as the exponential convergence rate.
I'm sorry,
Oh,
can
yeah.
I ask a question?
Yeah, sure,
Uh,
sure.
can you go back to page 22?
22?
Yes.
Yes.
Uh, I'm sorry, maybe 20. One.
Anyone? Yeah.
Yeah, so here with Hilda and you solve policy equation via neural network,
Exactly.
and the PN is the error from the neural network
Hmm.
at level at iteration n.
Right.
So I'm wondering why the error do not accumulate. For
That's
example,
that's actually a
P
really good question. Yeah.
why not Pn minus one does not appear here? Why
That
they all disappear?
that's actually a really good question. That which is also pointed out by Professor Hong. The one reason is that so we are going to decompose the approximation with residual part and policy mismatch part and iteration part. And from my observation is that because of the linearity structure, the error is propagated just linearly. And then such accumulation is controlled by the contraction rate, the smaller than one, on the very small time interval t, and we can patch them. So that's my short answer to your question. So do I address your concern?
So, I mean, in other words, you're gonna tell us about the proof, right? And then we can.
Yes.
Oh yeah.
Yeah. Okay. Okay. Yeah. You can show us. No, no. Keep going, and then we can observe it and understand it better, and then we ask you more.
So to show the exponential convergence, we observe the difference between value function in the iteration and defining the delta of n as the difference between those two. So using the linearity, we have the following linear PDE where L of n is defined via the current policy and the next policy and current value function and next value function. So to use parabolic estimate, we first estimate such a quantity L of n, and by the regularity property of the Lagrangian, the difference between the L of n is controlled by the uh, gradient norm of delta n and then delta n minus one. So following the energy estimate and parabolic smoothing, we first get the estimate on the left, and we also get so here the supremum is over time, and we also get the uh, pointwise pointwise norm estimate of gradient of delta n. So by taking t small enough, we get something like a contraction. So applying this iteratively, we end up getting L2 norm decaying exponentially. So uh, now getting back to our main result, where we show the approximate solution converges to V with with the precision controlled by residual loss and how many times you iterate it. To see this, again, we focus on the residual. So residual is the quantity determined by the V of tilde. So here we need subscript small n. So at each iteration we get residual, but the residual is controlled by the optimization, meaning that with finite number of samples we optimize neural network to minimize all events. So in practical application, Ln is the L2 norm of Rn is usually controlled very low. And at the same time, V and head is defined to be a exact solution with a approximate policy. So with a neural network, we have a policy update. So we have two tracks of policy. So one follows the exact iteration, and one follows the approximate iteration given by a neural network. So we had really bridges them together. So we had is a viscosity solution with a approximate policy. And we decompose the v and tilde minus v into three parts: the residual part, policy mismatch part, and iteration error. So the last part, iteration error, is controlled by the theoretical result introduced earlier. And the residual is just controlled by R of n, L2 norm of R of n, which is assumed to be controlled well. And the policy mismatch part is controlled by some differences between here. The policy mismatch part is controlled by the gradient of approximate value function and true value function. And this quantity is also controlled following the similar argument in this part. So part we can estimate the source term in terms of the the gradient norm, and then we take t small to make contraction happens. So I would say that's a very important and critical idea when proving this property. And combining all together, we get such a rate of convergence.
Excuse me, can you go back?
Yeah, yeah, yeah. Here?
Yeah, so in step two, it should be
Mhm.
V hat instead of V tilde, is that right?
Yeah, yeah, yeah. So I wrote them very roughly. So you get we had, but we had gradient we had minus we had my gradient v hat minus v uh, is con is also controlled in a similar manner. So when you control
Uh,
v hat and vn, you go back to v tilde and vn. V.
if you want to control gradient of V hat with gradient V tilde, this seems to depend on Pn minus one.
Yeah, but when you iterate once more, you get contraction factor one more time. So
You don't
adding them
have
up together.
contraction of Pn minus one on your left-hand side. On your left-hand side, it is only for subscript n. You don't have contraction for Pn minus one. And also in step three, I don't understand because here V tilde also appears. It seems that Pn or Pn minus one should also appear here.
P here.
Yeah. So I have trouble understanding your both step two and step three.
Mhm. Uh, yeah, actually, I skipped lots of like details in
And
this.
can you show your paper if you
Oh
can
yeah,
show,
yeah, sure, sure, sure.
because
I think
yeah,
that's
this is an important question.
so.
Because when I read it, I saw that every step you have the contraction matter, and when you sum it up, there's a geometric series. I mean that's what I read when I read his paper. Or maybe can you go through the experiments and go back to that question by the end?
Oh yeah, 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 sure.
Yeah.
Then I'll
How
quickly go
about that,
through.
Paul? Is it better?
Yeah, yeah, yeah. That's. Do
Okay.
you see the screen?
Yeah, yeah. You can do this, and then yeah, no, show us the experiment and then come back to that question.
Yeah, yeah, I'll do that. So we have conducted experiment on 2D, 5D, 10D problems. In 2D problems, so let me show the situation. So you're given a the color points indicate the initial point, and they are um, they and the black dot indicates the target, and the agent is the agents starting with those color points aim at approaching the target point, while there's a obstacle denoted by the red dots circling around it. And so we want to control such a point into the target point. So avoiding the moving obstacles. So as you can see from here, as time goes by, the color points head to the target points, trying to avoid the moving obstacle. So like this. So this problem can be written in terms of a differential game framework. So we want the cost function is determined by the cumulative action cost and how close the terminal point is to the target point. So using the framework introduced with a proper amount of the diffusion, we get such a result. So I think it's also good to mention how can put the boundary condition in a hard manner strictly. So by writing our ansatz function as a sum of the terminal function and the neural network, the boundary condition is satisfied automatically. And this is, plots show how well our approximate solution, our neural net solution approximates the true solution. So since it's two-dimensional problem, reference solution can be computed quite efficiently using finite difference method, and the very last row indicate the relative error. So as you can see below here, the relative error is quite small. And this is a result, the simulation result obtained by a by synthesizing the optimal control using the value function learned. And another problem is publisher subscriber gain problem. So in that problem, we have one central agent and large n-1 subscriber agents. So subscriber agents tries to stay close to the publisher while facing the disturbance. So the dynamics is given like that, where nonlinear interaction between agents are described using the nonlinear function like that. So as a reference solution, when diffusion is isotrophic, so it is known that the optimal value function is represented as a sum of two-dimensional value functions. So even in high-dimensional space, we have a clear reference function. But if one's problem becomes anisotrophic, such a reference solution is not available. So in that case, we are going to use some kind of a perturbation argument to see how well our algorithm works. So like that, so for anisotropic case, we introduce a small perturbation determined by epsilon, and by decreasing epsilon step by step, and see how the solution changes over epsilon. So in 2D isotropic case, the column indicates the time. So at time t equal to half, we see all solution matches. On the other hand, as here, when time t is equal to 0, we see that the reference solution, the second row is computed using our algorithm, and you can see that it matches well with the reference solution given in the first row. And the last row is determined is a solution from a direct physics-informed neural network approach, which means that we have Hamiltonian, and we throw that Hamiltonian into the physics-informed neural network framework directly. But our observation is that when you directly dump that PD into physics-informed neural network framework, the solution is not that accurate. So comparing these two rows, the first row is from our approach, and the second row is from the direct PINN approach. So you see a significant reduction in error when you use a policy iteration. So for 5D case, 5D case with a varying epsilon. So as you can see, as epsilon decreases to 0, you can see that it matches the reference solution, analytical reference solution, which is a given as sum of two-dimensional value functions. And same happens in same result can be obtained in 10-dimensional space as well. So to summarize, we propose a mesh-free conversion policy iteration algorithm, which works pretty well in two-dimensional to 10-dimensional spaces. And using the similar structure, we have handled a stochastic optimal control via neural policy iteration. And we also dealt with exploratory Hamilton-Jacobian equation using following the same philosophy. And those two works have been submitted to AAAI last week. So yeah, this is the end of my talk, and thank you for the listening. So should I get questions first and go back to Paul's point, or?
Yeah, I think you should go to Paul's point right away now.
Oh yeah, sure.
Thank you.
Yeah, that's an important point because I also when I saw the preprint I was also curious about that.
Okay. So do you see the
Yes,
screen? The script?
yeah.
So here it's the convergence of theoretical solution part. So the Lagrangian can be decomposed in these forms, leading to two source terms like that. And the En of n is the maximum of the L2 norm space L2 norm. And dropping this, we get this first, and then the parabolic smoothing part gives you this bounded by Fn and Fn minus 1. Here you take the t small enough again, then we get the control of f of n. So you start from here, and then using this bound, so that's cancellation thing. So something like cancellation occurs here by rearranging. So Fn is exponential, so En is exponential, decaying.
Yeah, that part is okay, right? And then can you explain the PN part?
Oh yeah. So we follow the exactly same argument. So here's the difference between Lagrangian with this and the approximate policy. We estimate that with intermediate term. So we end up getting this one and this one, right? And then we apply the same parabolic and L2 estimate with this to get this, and then which requires this, and this one is also estimated in following the same procedure. So end up getting V tilde n minus 1, 2, and V tilde n minus 1. And combine them all together, we get a recursive relation with Fn. And here, we also take t small sufficiently small to make contraction happen, like say less than 1/4. So the residual error only appears in this part.
Can you go down to page 12?
12, yeah.
So you change rho to some rho tilde that
Yeah.
taking into account both eta and rho.
Yeah.
Do you have does it answer your question, Paul?
Uh, uh, I don't know. I probably need to read the paper. I
Mhm.
still feel quite strange. So, but maybe I'm wrong.
Yeah, so can you go up to 11 again? Because so there was a question. I mean, when you take the ln, right? The
Mhm.
to take the error,
Mhm.
um, so you have the gradient in v and tilde minus v and the gradient in v and hat minus v, right? You have both of the terms.
Right.
And then by taking t small,
Mhm.
uh, you still have the iteration.
Right.
Okay. Yeah, okay, maybe the best way is that go ahead.
So maybe what I don't understand is how v hat minus v. What you can do about that? Because they have completely different controls.
Yeah, but here we had, so you see, by putting intermediate term like we had alpha and Vn, you see
Mm-hmm.
there's a uniform Lipschitz of L, so that this term minus this term is controlled by policy update, alpha tilde n and beta tilde n, and alpha n beta n. And the difference between those two policy is controlled by the value function in the
Oh
previous.
no, it also depends on your arrow. That's not true. It also depends on the arrow.
No, 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 no. Alpha tilde, beta tilde are just so we show that the update method is Lipschitz. So here,
Right,
oh no, PD comes into play.
but your alpha tilde, beta tilde, they depends on your arrow, no? If you have different PN, alpha and beta and they are different.
Can you go to the definition of alpha tilde and beta and tilde? Alpha and tilde and beta and tilde.
Mm.
Yeah, because I think if you have the gradient, that I think it's agree. The question now is what's the definition of alpha and tilde and beta and tilde? Because the moment you put it in
Right, right.
the error,
Alpha and tilde and beta and tilde is defined by this process, fixing P equal to gradient. Uh, ah, maybe I'm confused a bit. Alpha tilde.
Mm,
So here, I'm not here.
alpha and tilde and beta and tilde. I think you said that it comes from the from the neural network that I that
Mhm.
um just like what's the definition of alpha and tilde and beta and tilde, right? I mean that
Alpha and tilde and beta and tilde is defined here
okay.
with V and tilde.
So with V and tilde, then you define alpha and tilde and beta and tilde, and you said there's no
no,
error. Oh,
there's no
Ah,
arrow.
yeah, I get the
Your
point.
arrow should play a role here.
Yeah, I think this estimate should be fixed. Yeah, I
Right,
there's something.
something should be fixed.
Yeah, yeah, I think I should do it right away.
It's okay.
Yeah, thank you for pointing it out.
yeah, it's okay. I think in a way that when you have the error, but if you have the iteration with the geometric series, and it can go away
Mhm.
in some ways. Yeah, that's a point. Okay. Okay, so let's first thank Jonan for a nice talk. Thank you. And
Thank you.
yeah, and thanks for the great question. We still have a bit of time for some further questions in 4 minutes before we go to uh, um, informal discussions. I just want to point out that it's actually Paul who brought me to policy iteration. So Paul knows all this question in policy iteration, and then he was
I think you
bringing.
know better.
Yeah. Okay. Any questions for Yeoneung? maybe can you go to even just a definition of policy iteration, because I think this is new for some people here. It's hard to see what's the meaning of policy iteration. Yeah.
Smart.
Yeah, just stay there. Any questions for Yeoneung? Oh, okay. So if there's no question, let me ask you just one question, because there's a thing there that I think that can be fixed. It's not a problem, but it's a great question from Paul. My general question is that I have seen, I mean, many people who have solved non-NDPD by using neural network. What they do is you said it by the end is that they just dump the whole PD into so say you solve the equation f of u equal to 0.
Mm-hmm.
What you do is that you minimize the L2 of f of v square d.
Yeah, right.
So you just dump everything into a loss function and you solve it. And you
Mm-hmm.
did explain by the end that you also try to do it. Uh, from your perspective and from the actual seeing from what the neural network does, what's the advantage and disadvantage of that?
That's actually a really good question. So I would say as a uh, as a mathematician, I still don't think that this framework is complete. So we don't compute the L2 norm in the whole domain. We just approximate it with some sample points. There's a still theoretical gap here, and advantage is that uh, 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 even if we use only finite number sample points, because due to the intrinsic regularity property of a neural network and solutions of PDE, such a point Monte Carlo type approximation is quite efficient, provided that there are many successful cases of this approach. So I think that's a one uh, an advantage and disadvantage at the same time.
Hmm. And there are many people also told me that there can be many local minimum
Hmm.
that your loss function might get stuck with
Hmm.
if your equation is not convex. That you see that in your sort of numerical or the pins computation.
In at least in our benchmark cases, I haven't seen such a phenomena. Meaning that we are this the experiment all sets of experiments went quite smoothly without uh, failing to have a isolation point or non-local optimal. Uh, and I think that's a another good advantage of this approach.
Hmm.
So it's still possible that solution falls into local minimum instead of a global minimum, but in many practical regime, it does not happen that does not happen that often.
Hmm. So the very last point is that you can solve it in 10D. Are there competing approaches with you at this moment? Because
For this problem, as far as I know, that's very first result on that problem. So the no one have considered a stochastic type finite horizon uh, zero sum differential game with pin iteration.
hmm, okay, great. Yeah, because I have not seen any FEM or FDM in 10D. So okay, yeah. So let's thank Yeoneung again. Thank you.
Thank you.